Right, so example 1, they ask us to sketch the solid whose volume is given by the integral and evaluate the integral. Right, so maybe a good idea would be to pause the video and then attempt this on your own, and then should you get stuck, you can hit play and I can guide you through it, but it's important to think about it first and envision what this region looks like geometrically, seeing as we are new to cylindrical coordinates. Right, so we are given that r runs between 0 and 2. Theta, all of them are in play, 0 to 2 pi, and then the z's run from 0 to r. And then the function we are integrating is simply r, and for that reason we arrive at the volume of this solid E described by the limits of integration, right? Okay, so that is because the function that normally adds height, therefore taking volume and adding a dimension to it, since the function we are integrating really is the constant function, there is no height added, meaning the volume doesn't have a dimension added to it, it just stays volume. The part that confuses students is saying, but there's a function in here, we're not integrating the constant function one. No, there's not a function in there. The r forms part of the formula for a triple integral where we use polar coordinates, remember? So the integrand really is the constant function one. So that is why calculating this integral really gives us the volume of the solid E over which we are integrating, that's given by the limits of integration. Right, so let's start dotting this down. So this is what we are given. All thetas are in play. Right, and Z is between 0 and R. Right, so we notice from this that we are only dealing with positive Z. And how else should we view this? Well, we can express R in terms of theta or x and y. So the inequality, Z being less than R, really means this, right? If we express it in Cartesian coordinates, and we were also given that R is not anything bigger than 2, right? So that limits of integration for Z mean only positive Z, and Z is at most 2, since Z depends on R, or it's bounded above by R, and R is at most 2. Right, so think about what you are supposed to sketch. What does this solid look like? What happens for the projection in the xy plane? All thetas are in play, so we're going around the z-axis, and R is anything between 0 and 2. Okay, and then for Z we are starting from the origin upwards, and we are staying inside of this cone, right? Where we stop this cone at value 2. Right, so what am I sketching? So you have a cone opening upwards. It should stop at 2. And the z's are everything from the origin to the value 2 inside of this cone. Right, so that's the solid. We're looking for its volume, as explained earlier. The volume of the cone is actually given by this integral, because we are integrating the constant function, therefore we are not adding a dimension to volume, we stay at volume. Don't get thrown off by the r, thinking that is the integrand. That's just part of the formula, since we are integrating over a polar region with some height added to it. That r comes from the polar region's area. Right, and then this shouldn't be a hard integral. So we integrate with respect to z first. So that means a z is added, and subbing in the limits takes me there. Then we go to theta next. So that means r squared has a theta added to it, and subbing in the limits takes me there. Right, and then finally we integrate with respect to r. And subbing in the limits takes me to the volume of that cone. Right. Let's move on to the second example. We want to evaluate the triple integral over some solid E. E is the solid in the first octant that lies under this paraboloid. Right, so the first thing to do is to envision the solid E and decipher which method would be most effective, meaning how should I express this region, Cartesian coordinates, polar coordinates, cylindrical coordinates. What is the projection in the xy plane, type 1, type 2? So most of the hard work lies in finding the limits of the integral. After that, we're really just asking whether you can integrate, and hopefully the answer to that question is yes. Right, so what do we do here? We think about the projection of this paraboloid onto the xy plane, and that will enable us to find a restriction on x and y, which may or may not be easier to express as polar coordinates, and then we figure out the height that is produced by this paraboloid, giving us the z values. Right, and keeping in mind we're in the first octant, so we should really just work with positive x, y, and z. Right, so projection onto xy plane. So that means z is 0. So we have a circle, radius 2, which means we can express it with polar coordinates. All thetas are in play, and r is between, so we're staying inside this paraboloid, so r is between 0 and at most it can go up to 2. The other thing we should remember is we're in the first octant, which means not all thetas are in play, only 0 to pi over 2 thetas. Right, and then we should think about Z. So the solid that lies, E is the solid in the first octant that lies under the paraboloid. So Z is restricted by the paraboloid. The highest it can go is the paraboloid. And the smallest it can be is 0, because we are staying within the first octant. Right, which means we can express the integral now. We have theta on the outside. So remember, in this instance, theta and r are not dependent on one another. Typically, r is dependent on theta, and then you can't just swap the order of integration. But here they are not, so you are free to choose the order of integration for r and theta, not for z, because z is dependent on x and y, which is dependent on r and theta. So you must integrate with respect to z first. So first octant means the lower limit is 0, and the upper limit is the paraboloid, right? Which you should express in terms of polar coordinates, which, lucky for us, is easy to do. Right, then the function that goes in, all polar coordinates. So you have x plus y plus z. We do not change the z. And then do not forget about the r that forms part of the formula. And that means the hard part is done, hopefully. We can integrate this without too much trouble. Right, so we have no choice in integrating with respect to z first, but thereafter you might ask yourselves whether it's easier to integrate with respect to r or theta first, because you can swap it in this instance, but that really doesn't matter. It's probably the same amount of work either way. Right, so let's integrate with respect to z first. So a z is added to this. And there's a double r, and then in goes the limits. And since we're integrating with respect to r next, you may want to expand all the multiplication and the brackets that happen here before you do the integration. Right, so I would recommend doing that first and then integrating. Okay, then in goes your limits, and then finally we integrate with respect to theta. So again, cleaning up before integrating can save you some of the work. And then in goes the limits. Right, that being our final answer. So again, I emphasize that the hard part lies in establishing the limits that occur from your solid E, then reminding yourself that R needs to be part of the integrand you're integrating after you've converted to polar coordinates, and then the integration, take it step by step. Don't forget all the things you learned in first year. Right, then we can get to our final example, where we have to find the volume of the solid that is enclosed by the cone and the sphere. Alright, so again, if you read volume, you should think triple integral. Right, and now they give you a solid that is described as being enclosed by these two surfaces, meaning that produces this region E, or the solid E, over which you're integrating. Now, how do I also get the volume of the solid E over which I'm integrating? Well, you take your integrand as the constant function, okay? But that, so this is what I mean. But now, right, so this gives volume of E, but now when using polar coordinates and thinking about the volume of the region over which I'm integrating, if there's polar coordinates involved, it means I have a variable R that forms part of the formula, so it's part of the integrand. So after I've come up with this solid E, if I use polar coordinates, I have to use that R forms part of the integrand. Right, do not forget that. So how do we deal with this? So you should think about a cone opening upwards and then a sphere that at some point intersects it, and we are interested in the solid that lies above the cone and below the sphere. So we have to get the intersection and then do the projection of that onto the XY plane. Figure out what that looks like. It may or may not be easier to express it as polar coordinates. And then deal with what the height is, what the z values are. So we know the lower bound should be 0, right? Or did I maybe speak too soon? Right, so think about what you are envisioning. Let's maybe start with the easier part. So projection. Of the intersection onto XY plane. Right, so we have the intersection as this curve. So z squared means I add this, and that reduces to this circle, right? So the projection of the intersection onto the XY plane is a circle, easy to express in terms of polar coordinates. All thetas are in play. And r can be smallest 0 and biggest 1. Right, so we're happy with the polar coordinates. Now we have to think about what happens for the z values. So you have a region enclosed by two surfaces. So the z values would have to be restricted by the lower surface, which is the cone, and the upper surface, which is the sphere, right? So that takes us here. We get the volume by integrating the constant function over this region E, but now we've expressed E, or the solid E, with polar coordinates, which means we are not integrating the constant function, but R, because R forms part of that formula. Now, which z limits am I subbing in? So it's the lower surface expressed as polar coordinates, of course. So that's the cone. And then the upper surface, so solving for z from the sphere in terms of polar coordinates takes us to that expression. And then the integration can happen, which hopefully won't be too hard, seeing as the integrand is simple. So you have a z and then subbing in the limits takes you there. Right, then up next we integrate with respect to r. Now the second part is easy. How about the first part? Well, you sort of have the derivative of the inside on the outside if I compensate with a constant. So I can do this. So I just integrate normally by adding 1 to the exponent and dividing by 1 over that after I've compensated for the constant, the missing constant, and then in goes my limits. let me just correct this mistake. So it's already r squared prior to integrating. So therefore we go to r cubed. Right, so now we can integrate with respect to theta, so that really just adds 2 pi to the mix. And let's see if we can clean this up better. And that takes us to the volume of the solid that lies between the sphere and the cone. Right, so that covers it for cylindrical coordinates. On Thursday in person, we will cover spherical coordinates, taking a very similar approach to today's lecture. So we cover the idea behind it, and then we tackle examples to try and get a feel for how to express solids in terms of spherical coordinates, and then do the hard work of calculating triple integrals as well as volumes of solids that can be expressed via spherical coordinates. Since cylindrical coordinates make use of polar coordinates, the theory or the introduction to this lecture wasn't very long, because we could use a triple integral formula we've derived earlier. However, for spherical coordinates, we would have to think about the triple integral first, derive its formula, and then start using it.